All right, hello. Well, welcome to the control workshop here in DSS. So basically in this workshop, what I'm going to try to show you is sort of like the grand, like high-level picture of what you're in for when you want to use control. And sort of what I hope that you get from this talk is basically the foundation of what you are going to be dealing with when you start using control. We have killer documentation for a lot of features. So basically what I want you to get from this is just being able to go to this documentation and be actually familiar with the whole process and know what to expect. So, but first things first, who am I? I'm Juan. I'm a verification engineer at Runtime Verification, where control is from. And yeah, we're a formal methods company. We do formal methods for Ethereum, also for other chains. And yeah, you should check out our work because it's very, very nice. The way to get control, you can just run this bash command to install KApp, which is our package manager for our frameworks, and just you can use control from there. And also there's a repo with the examples that we're going to be showing in this workshop. You are not required to get the repo for this presentation, but you can recreate the examples from there. So this is where your control journey starts at this very moment, and it starts with read Jesus or Foundry, right? So basically, if you know Foundry, that's basically what you already know how to write control proofs. Like that's because basically control proofs are 100% Foundry compatible. And so basically, you can take any Foundry test that you would fuzz over, and then you can run it as a control proof, right? And you will be executing it symbolically instead of concretely, and we'll see what that means a bit later. So the way to basically take a Foundry test and then turn it into a control proof is you swap. Instead of forge build, you just have control build, and then instead of forge test, you have control proof, right? And these two commands basically do what you would expect them to do. In Foundry, to run a test, you need to prefix it with tests. With control, we actually have two more prefixes, which is proof that come from HVN, which is another formal verification tool for Solidity, and then we also have check, which comes from Halmosh. So this means that writing control proofs, it's compatible with these other tools, or you can also take these properties written for these tools and bring them over to control. So it also has great compatibility features. Also, as you would expect with something that's a Foundry test, we also have compatibility with cheat codes. We also have our own cheat codes. So besides supporting Foundry cheat codes, we also have our own. But also recently, Foundry have included some of which were our cheat codes initially into their cheat code suite. So basically, for the compatible Foundry cheat codes, you get mostly the most execution-related cheat codes, the way that allow you to manipulate EVM state and so on. We don't have 100% of the massive amount of cheat codes that Foundry has. The ones that we don't have usually it's because we haven't see that we need to use them. So if you're missing any, feel free to reach out, and we also incorporate them based on what our users need. So yeah, feel free to just reach us out. Also, we have our own cheat codes, which are because we're doing symbolic execution rather than concrete, right? So we needed our own type of cheat codes that was important for symbolic executions. So yeah, we added them, and one of the reasons why we initially have this, instead of having a test prefix, have a proof prefix, is because if you have custom cheat codes, they won't run as a Foundry test. So you want to separate them and not to break Foundry test suites. So with some of the cheat codes that are wrong, Foundry won't run, but this is big of an asterisk because Foundry recently added some of our cheat codes. In particular, these are the new cheat codes that were control inspired. This set arbitrary storage, copy storage, mock function, and then this random uint bool address and bytes. So the control equivalence, this is not exactly the same cheat code in the sense of the naming, but what it does, it's sort of equivalent brought to the realm of fuzzing. So set arbitrary storage for us, it's symbolic storage. For copy storage and mock function is the same. And then for the random, we just call them fresh, because in the symbolic context, it's not random itself. It's just a fresh variable. So basically, what set arbitrary stars does, in case you don't know, in Foundry, it just sets a concrete fixed number for any uninitialized or unread slots of a given address. And for us, it sets the entire symbolic storage, the entire storage as symbolic, right? Copy storage, it does with what it says. It just copies the storage from one account to another. We also support copying transient storage when needed. And in Foundry, as a caveat, you cannot use both copy storage and set arbitrary storage. We also have this mock function, which is sort of like a mock call, but on steroids a bit. So mock call would, the cheat code mock call would just swap a function call with a specified return value. In this case, mock function, what it does is mocks the execution. So it will swap the call with what you can consider a model of the function that you're mocking. And so that is useful if you have a very complicated function and you want that you want to execute just sort of like a model or a summary of it, but you still want to run it, not just get a concrete return value. And then we have this random, which is just in Foundry just a new fixed value, and for us is a fresh symbolic variable. So these cheat codes are not yet implemented in Foundry. They are sort of in the pipeline. So these are cheat codes that we still have, which is sort of, for Foundry, you have expect call, which is like, for us, expect regular call. But we wanted to also have some sort of more granularity where we're writing our tests. So in particular, we have these calls with these cheat codes, which are kind of self-explanatory. So basically, up to this point, why do we need to be so symbolic, right? Like you have Foundry, which fuzzes concretely and so on. So why is there need for symbolic reasoning? And well, a bit the reason behind this is that with concrete, like the state space is just too much big. So with symbolic reasoning, it allows you to actually explore basically the totality of it if you do it correctly, or at least a way bigger amount of the state space, and to ensure that your function has been as thoroughly explored as possible. And so, for instance, here, this could be like just a Foundry test, but what executing it symbolically allows us to do is to make sure that there is no value that's being tested that if this passes, there's no value that will make this test fail. Whereas with concrete execution, if you're fuzzing, you will never get to this level of assurance. So what is symbolic execution in this case, right? So as we said, for concrete execution, basically you just take concrete values, you start with concrete values, then you execute, and you always get sort of a concrete result. Whereas with symbolic execution, you can think of it as executing it as if it were variables from like a math equation, right? So you start with symbolic, in this case, for instance, if you're trying to somehow verify the behavior of the transfer from function, you will start with symbolic values for your pre-state, then you will execute with some symbolic values, and what you will get is an execution branch, an execution tree, where each branch basically summarizes a lot of behaviors that can be done in like a lot of concrete tests. And in this case, you just get like, for instance, in this example, like what if in the transfer from, what is from is different from to, and what if they're equal? And then what you get is like a mathematical evaluation of this and sort of like a symbolic summary of what's the behavior of your function going to be. And so, as we said, symbolic execution, you're executing, but in a symbolic way, sort of like, just think of it like variables in a math equation. And you start from a symbolic state, and you end up with a bunch of symbolic states, each of them symbolizing where can your function end. And so, taking also one step back, it's like, so what is formal verification, right? More broadly, formal verification means like you assert properties of your code, which is called specifying it, which in the case of control, you can do it with a Foundry test, with a Foundry property test, and then you prove, that your code actually satisfies your specifications. There are a lot of techniques to do this, like to take some specifications, some blueprint of what your code is supposed to do, and then doing some mathematical reasoning on it to make sure that your code actually follows these blueprints. Symbolic execution is just one of them, where we execute your code, as we said, symbolic parameters. Then you get all this branching, and basically you just get like like what's your function actually doing, and then we check that for every possible path, execution path that your function can take, your specifications, your blueprint is complied with. So it's also the case that there are many techniques for doing formal methods, formal verification, and there's a spectrum, right? Like they vary in the degrees of automatization, and they also vary in the degrees of which is the problems that they are able to solve. So meaning what's the kind of statements that you can prove. And usually, as a rule of thumb, the more complex, the more automated a proof is, or rather the other way around, the less automated a prover is a tool for doing formal verification. Usually this translates into the ability of proving more complex problems. This is also like sort of like a rule of thumb, but basically there's this spectrum of the least automated you are, usually the more like general problems or the more complex problems you're able to tackle. It is also true that the more automated you are, the easier to use it is, right? And especially for the kind of problems that it's automated to solve, these tools are really fantastic for just ease of use and just to get you going. And I wanted to give you some like examples of how does these different sort of proof systems work, right? So basically you have interactive theorem proving, which is like the most automated thing that you can get, which is like mostly manual, and you also rely on constant feedback from your tool to let you know where you are, and it requires a lot of user input, and usually the learning curve is quite steep. And then you also have automated reasoning, which usually doesn't require any interaction, hence automated. And it's also usually the case that you don't have any insights into what is the proving process. So it's sort of a bit like a black box in the sense that you query it for a proof, saying, I want to prove that my function something. And then it will say yes, no, but there isn't as much insight as with the interactive tools. So for instance, here's an example of an interactive tool. It's not very important what it says, just so this Lim4 is what is called an interactive theorem prover, and in particular this proof proves that if a graph is Hamiltonian, then it's connected. We don't really care a lot about this, but the thing is that with interactive theorem provers, you can get as far as into formally verifying virtually any type of math, like not just programs and functions, but like literal theorems about very complex things. This is what a proof looks like there. Like the statement is like the first and second line, and basically the user needs to fill every other line here, which it doesn't look very intuitive. And the type of feedback that you're being given by the machine while you run this looks like sort of like this. So you can tell that there's somehow a steep curve into learning this sort of stuff. It's also very rewarding in the sense that it allows you to go very deep and prove like arbitrarily complex properties about math or your code, or you have it. Then we have automated proofs, in this case, just with Halmosh, and this is how an automated proof looks like, in the sense that you just run it and it says if it passes or not. If not, it gives you a counterexample. It is also true that with automation, it means that you can get unknown results, meaning that the tool may just run out of time and saying, I tried to prove this automatically. There's some bounds of time because the tool is not going to be running forever. And if it doesn't find a solution to it, it will just say, hey, I didn't just find the solution for this. And then I want to give an example of control, because control is sort of in the middle. It's automated, but it's also interactive. So this is one example of what a control proof looks like when it passes. So it just sort of like, it looks like automated, like you just run it and it passes or not. But we also get feedback, which is one of the key principles that you need for an automated procedure, right? So in particular, with control, the type of feedback that you get is this tree that's made of all of the possible execution paths that your function can take. In particular, here we're seeing a branch where it tells you which is the path constraint that you're traversing, right? So for instance, here it's telling us that y is different than 0, and that x.y it's less than max u into 56, so there's no overflow in the multiplication and so on. And so basically, like, okay, I'm executing the function in this context. And what we see here are nodes. So basically, the nodes are snapshots of the execution at a given point. And in these nodes, what you get is like the full state of the OR formalization of the Ethereum virtual machine. So you get this sort of HTML-looking configuration, and here it's contained all the information of OR formalization of EVM. So basically, here you have we go like with cells, right? And so the KSL, for instance, it's OR formalization of the execution of EVM, and then you have things like the schedule, which we default to Shanghai, but we also support Cancun, and changing this is just one command flag away. You also have the output. You also have caller, call data, and so on. Word stack, local memory. So basically everything that you would hope for when executing. Like, okay, what's the state of my smart contract when I'm actually running this function? And then we also have the interactiveness part, right? So because here. So the way this goes usually, it's like you execute it, then you inspect a bunch of states, and then you say, OK, this is telling me that my function is behaving like this. And then you can tell control to say, OK, now I require you to reason about this in this specific way, and we do it through what we call lemmas. We'll go over this in more detail later, but this is basically what interacting with control looks like. It's writing these files that then control will parse, and then we'll reason with taking into account what we wrote. Here's also a sort of like a snapshot of this is a non-exhaustive list of formal verification tools available for the Ethereum ecosystem. But yeah, we luckily in this space we are not short of tools, and there are fantastic teams working on formal verification for this. So I heavily encourage you to take a look at every tool, because as we said, there's like a spectrum of automation versus ease of use versus kind of problems that you can solve, and so there's one tool for each job, I would say, or at least for the kind of verification that you want to do. So yeah, definitely check them out. That's nice, but this is a workshop, so let's get some work done. We're going to be verifying some stuff with control. So first things first, I want to talk about hardware requirements, because control is quite resource intensive, and we've had these cases in the past where it seems like control is crashing or failing, but it may be that it's because of lack of resources. So we require a minimum of 16 gigabytes of memory for things like building and so on. There's some caveats, like if you're using this Windows subsystem for Linux, I think it by default only allocates like 2 gigabytes to it. So you should look that up and make sure that you have, if your machine has it, at least give 16 gigabytes of RAM to it. And same with Docker containers. I think in Macs it's also capped like at 2 gigabytes or something. So just make sure that you have these requirements like set up. And also for running proofs in parallel. As a rule of thumb, we're like 8 gigabytes of RAM per proof. This is not like, you can experiment with it. Your computer is not going to burn or anything. But yeah, this is sort of like what we look to usually. And so this, you may feel, if you've ever tried control, you may feel a bit represented in this picture, in the sense that there's a lot of options and there's a lot of things that you can tweak with it, and it can be a bit overwhelming at the beginning. So I'm hopefully trying to give you some clarity into all of this. So this is basically how the interaction loop with control looks like. So you would start right at the build stage, right? You first build, then you prove, and then you inspect, right? So you build to, well, first be able to prove, but also to include new lemmas. This is one of the reasons to keep rebuilding stuff. And then when you prove, basically you will produce what I showed before, this symbolic execution tree. And basically, there's like a subloop there in which you inspect the symbolic execution tree, and then you can manipulate. You can, you can say, okay, you did something weird here, and I want to zoom in on this. And so there's this cycle in which you prove, you produce your symbolic execution tree, which is like the summary of how your function behaves, and then you can inspect this summary that control produces for you. And just sort of gain more insights into what's happening. And then out of those insights, then you may be wanting to write more lemmas to then include them again in proving. And this will make some sense in a moment, but this is like high level how the proving interaction works with control. So yeah, if you just go and do like control build help or control proof help, you will be bombarded with all these options. And sort of, if you try to sort of understand which ones are the ones that are more useful to you, again, it can be a bit overwhelming. So let's start with control proof, build, and see among all of these what is really important for you as a user. So basically, the important options revolve about including including lemmas, basically, excluding some if you want to, and also regenerating K definitions, which this is used to include new lemmas. So basically, to include auxiliary lemmas, we have this flag, auxiliary lemmas to control build. At the bottom, you can see sort of the command that you would need to put to execute this step. These auxiliary lemmas is just things that we have encountered and working with the tool, and we found very useful. So this is just also sort of, if your proof is not working from the beginning, this is something to try right away, because this enhances control's ability to reason. Then you also can include your own lemmas. We do this with this, require, and then a path to your K file, and then the model that you want to require. This is not important that you memorize any of this. It's just so that you know how it looks like. Then we also have some catch-hack lemmas that are included by default in control. You can also exclude them, but they are basically working assumptions on how the catch-hack should be. Basically, we assume injectivity, and we assume some collision resistance from symbolic values. These are not mathematically sound, and this is why we include them as a separate part. These are not part of our core semantics of EVM. But these are working assumptions that we need to do in order to be able to reason effectively about EVM code. And then you can also just regenerate K definitions in case you include some lemmas with regen or recompile. So this is a bit of how the full control build command looks like. And also, we have control proof. So again, control proof has even more options than control build, and so it can be really daunting to just go about it. Again, the relevant options are for proof execution tweaks. So it's just getting, zooming in into the execution trees, doing some loop exploration behavior, and also to increase the performance of control. To get, more detailed execution trees, remember we have a node. So an execution tree is basically its paths based on branch conditions, and then we can specify when do we want to create a node, which is like a snapshot of the entire state of our EVM while executing your function. And so we have a lot of, rules to create new nodes. We have max depth, which basically means after doing X steps of execution, just make a snapshot of whatever you have. Then we can also specify when do we want it to break in terms of, for instance, AVM opcodes, either every AVM opcode, every jump I. We also have now jump. We can also, like, if you say, like, I want to know where I'm jumping to a function or when I'm jumping into a loop or whatever, you can break on jump I will allow you to create a KCAG where you have snapshotted every time you did something like that, also on storage and on cheat codes. We also can change the loop exploration behavior. So one thing that's in control by default, we don't bound loop execution. This means that if you have like an unbounded loop, you can get an infinite a potential infinite execution tree. And the way we do it, we allow bounded loop reasoning in control via this BMC depth command, where you specify how many loop unrollings you want to get. So basically, you will enter a loop, and then you will execute it the amount of times you specify, and after that, it will just conclude the proof and give it as passing. And we can also specify loop invariants, which is sort of like the other way of tackling loops, which is instead of just unrolling a finite amount of times, you can actually specify what's the expected behavior of your loop, and then control will take that into account. And then as per Control 1.0, which we released some months ago, we also have this optimized performance flag, which will just make things faster, and you don't have to take, you don't have to tweak some parameters yourself. It will just get the faster execution running. And it will also do like parallel branch exploration, which you can set the number of how many branches do you want to explore concurrently. Again, this depends, like the number of branches that you can explore concurrently will depend on the hardware that you're running this with, but yeah, just keep that in mind. Okay, so you just control proof something and it passed or failed. Now we need to inspect what control gave us back, right? So we have basically two exploration commands. One is control view KCFG, which is a terminal UI interactive viewer where you can click on the different nodes and see the different state snapshots that it took. And there's also control show, which is just plain CLI output. And also, we are introducing K as a service, which it also gives you a web view of your proof, and it's a very nice web view. And so, yeah, more on that also later. Once you've seen what your proof looks like, you can also do some manipulation, which basically means you can remove nodes. You can, say, I don't want to explore this branch anymore. We'll see some more of that later, but I just want you to get with, like, the main point I want you to go with, it's like you really can inspect everything you want about your function execution with control. Then you can, manipulate what the snapshot looks like and start reasoning from there. So maybe you're a bit like this after, all this mambo jumbo. So just remember, what we're doing here, basically just these different steps where we're either including lemmas, we're proving and then producing these symbolic execution trees, and then we're manipulating them, we're expecting them, we're doing a lot of things with them. And out of all that interaction, we can write new lemmas that will make our proofs advance further. OK, so now let's apply the verification cycle that we just shown. We're going to be working with this example, which it doesn't look very super interesting at first, but it will tackle the whole thing. And it's a I think it's a very complete example, as in how is the complete usage of control looks like, right? So this basically is just adding numbers from 0 to n. So we start with n, then we have these two variables set to 0. Then we go into this loop that we just add 1 to I, and then add I to result, and then we return result, right? So what we expect intuitively is that sum to n of n is actually the adding numbers from 0 to n, which coincidentally this has a very nice mathematical closed formula, which is this one. We won't be showing this in the proof of this statement in the talk. There's a very nice post that Raul here recently did about formal verification on loops, and the proof is there. So I encourage you to go to our blog post page and find it. And so after looking at this, we would expect that our specification for the proof sum to n looks something like that, right? So with this in mind, we can just build it and then just try to prove it. And as I said before, control by default doesn't bound any loops, and sum to n is basically just one loop. And so what we would get if we just execute what we have here, it's something like this. So this is the execution tree, sorry, the symbolic execution tree that I was talking about earlier. So basically, you just get these nodes, which are just snapshots of what you have. And then basically here, you can see a jump I. So the thing also in control is that you're working with EVM bytecode. So even though you write your test in Solidity, what you're actually verifying is what your code is actually being compiled to. So here we see that we are entering the loop with this jump I instruction. And we also see that we're checking if n is less than 0. So basically, what this is checking, even though this is not exactly the condition that we put in, but the compiled code, what it's doing is checking, should I exit the loop, or should I continue and enter the loop, right? And so it's checking, is it n less or equal than 0? So should I just exit? And then control just branches, right? This is symbolic execution. So then control just says, hey, I don't know if n is less or equal to 0. N is a symbolic variable. So let's just suppose, on the one hand, let's just suppose it is. And then if it's less or equal to 0, it just exits the loop. We can see it exiting the loop here. And then it just says, OK, then I just finish. So for this branch, I do get to a successful state, and your test passes. And then it goes on and says, OK, what if actually n is greater than 0? Then we enter the loop. And then we execute a bunch more. And then we do one iteration, and we say, hey, now, what if n is less than 1? Then if that's the case, then we just exit. And if it's not the case, we're still in the loop. And then control will just do that again with 2, and with 3, and with 4, and it will just not stop. Why? Because we are not bounding loop execution here. So by default, control just will start to create this potentially infinite execution branch, right? Execution tree, sorry. Unless we at some point we stop it. But if not, as you can see, it will just get bigger and bigger and bigger. Here is where I stopped it. And so how do we go about this? Does that mean that we cannot verify this with control? Well, luckily, what we have here is that we can add some BMC depth. So we can tell control, hey, at some given depth, just accept the proof. Like, I just want to execute this symbolically, and if it has worked for the first 4 iterations, let's just assume it will work for the other, how many it could have, right? And so with that, it will pass. So I executed this proof with BMC depth 4. And we want to see how the execution tree looks in this case, which will look basically the same as what we just saw. But at some point, Again, it's branching, then we enter the loop, and then it says, oops, and then it says, yeah, sure, everything is fine. And then we will do that several times, and then right at the bottom, exactly. And then we get here, and then it's like, well, is n greater than 4? Should I enter the loop? And then it's saying, well, here I'm assuming it is, but I would be entering the loop a 5th time. So that's out of our, that's out of our bounds. And then it just cuts it and say, OK, I give this for every iteration that I entered, I successfully completed the test. In this case, I'm just going to end the test here because you told me so. And so that's fine. But for instance, what happens if we have, say, a malicious sum to n? And by malicious, I mean, like, what if, we are executing the loop, but it says, if I'm greater than 4, I'm just going to give you an incorrect result, right? Well, the thing, what happens here is the same, basically. You will, if we, I think I have it here. If we run this, oops. Sorry about the live demo thing. Yep. Well, you can see here, if you run it, basically it will pass. You will have the same amount of nodes, and it runs in basically the same amount of time. And so here what is happening is that the behavior that would make this proof fail, it only happens after a certain amount of iterations. And so how can we basically go about this, right? Yeah, if we execute it with this, basically we'll just succeed. So how can we solve this? Well, we can solve this with loop invariants. So loop invariants are basically their properties that are supposed to hold before the execution of a given piece of code and after the execution of a given piece of code. Invariants can also be trivial properties because something that holds before and after doesn't really need to be meaningful about your code, but you want this to be something actually meaningful about your code. So basically a loop invariant, you should craft a loop invariant in the sense that you should craft a property that captures what your loop is really doing. I will also say crafting loop invariants, it's a problem that is arbitrarily hard. Like this can be quite a challenging problem to face in the sense that, for instance, if you had a very dumb loop that it just computes, you just give it a number and it computes the nth prime number, like coming up with a loop invariant for that will basically grant you the novel equivalent in mathematics. So it's really like, it can be a very challenging endeavor, but Control supports it, and there are ways to sort of automatically or pragmatically come about with loop invariants. So let's just start forging the intuition here on how does forging a loop invariant for this look like. So when we start the function, we basically have that result is equal to I, which is equal to 0, which coincidentally is also equal to the closed formula that we hope this function to be equal to. And after executing the loop, we would get that I is equal to n, and then hopefully we would get that the result is equal to n times n plus 1 divided by 2. This is what we want to actually know. Like this is our intuition, but we don't know. And so these are sort of the loop invariants recipe when you're looking at Solidity code. So you basically look at the loop head, see what you expect the state to be. Then you execute the loop, then see how the state is updated. And then you sort of want to generalize that into a property that captures what is the state updates that your loop ends up with. This is for Solidity, though. For EVM, we have to do a bit some more extra work because we first need to identify where the loop head is because that's not super trivial to do when reading bytecode. And then we just, again, sort of inspect how the state is, see how it's updated, generalize it. It's very important with control. Once you come up with what you think is a sound loop invariant, control allows you to actually prove that your loop invariant is correct. And then basically you can include this loop invariant as extra knowledge to control to say, hey, my loop takes states that have this sort of form, and after executing this loop, it transforms it to this different state that has this particular form. And in this way, what you're doing is actually you're effectively summarizing the actual behavior of the loop, and you are sort of executing it to completion, which it gets rid of just executing a few iterations. You're actually encapsulating the entire behavior of the loop in this using this invariant approach, right? So first, we need a word about lemmas, because you need to understand how to write a bit of K, which is what control is based on, in order to feed it lemmas. And so basically, very quick, the files starts with some requires, which in here we import a formalization of how Foundry execution works and how EVM execution works. Then you just have this module, where you will have your lemmas, which are like these reasoning bits that control takes to enhance its reasoning power. You import some modules, and then basically here's like the meat of the file, which is the rules, or lemmas. So a rule basically just has the syntax: rule something, require something, and then simplification. For us, a rule is something that is a rule that has the attribute simplification, but yeah, basically just rule. Then you just write your rewrite conditions. This basically means, if you start with the left-hand side of this rewrite, in this case, bool toward x, you will rewrite it to whatever is on the right-hand side. So this is the rewrite symbol. So this tells us that you start with this state, and then you will end up with this other state. Then you can have a requires clause, which basically is just apply this, this transition between two EVM states. Just apply it only if the condition that goes after the requires clauses is fulfilled. It's not necessary to have a requires clause, but it's there in case you need it. And then it's just the simplification attribute, which is sort of like a particular type of rewrite rule that we have. Great. So let's prove the invariant, but first let's see how this looks. So we want to, in this case, we want to first inspect the configuration that control has given us, right? So when this loads, we sort of go here. Just as also a note, we executed this, if you remember from way before. We had this break on jump instructions, which basically tells when you are doing symbolic execution and you face a jump I want you to create a node, which basically a node here is just I want control to snapshot whatever the state is here for me to execute it. And we did this because since we're entering a loop, loops start with jump i's. So basically, we just scroll down. Also, sort of like a warning, sometimes you will have to aggressively scroll down or up due to the amount of information that controls gives you. But that's just something to get used to, and I think it's actually a pretty good thing. So here we are, node 27. We are at a jump I, and here we are splitting. So here we're branching. TLDR, this is our loop head, really, as we saw. It's seeing if n is less or equal than 0, and if it's not, it will just exit the loop, and if it is, then it will just enter, right? So I executed this with BMC depth 4, and here our goal now is to see, okay, I have this jump I here, node 4, and this is the very first time I'm entering the loop. And then if we scroll the way down, we can see, yeah, this is where it bounded. This is the last time it exited the loop. Here. This is the last time it exited the loop. And so basically what we can say now is, OK, give me so the way we're going to come up with the invariant is we're going to see which are the state changes that happen between the first time we were entering the loop, the first time we were at the loop head, and then the last time that we let control execute, the last time it exited the loop. So the way to do this is via this control show node delta. So what this will basically do is it will take two nodes, and it will perform the difference of what has changed in the EVM state between this node and this node. And if you notice, we're doing it with node 54, which is the first node that's actually jumped out of the loop. So if we just do the node delta thing, it may take a little while to just load, but it will basically give us, again, the entire configuration, and then at the very bottom of it, it will give us a configuration that contains the state delta here. So it contains basically what has changed between node 27 and node 54. And we can look at it by looking at these arrows. So basically, it said, okay, what has changed is, in the K cell, which basically is where the EVM code is executed, you went from this jump I on this condition to basically just jumping. And then if we scroll a bit down, everything else stays sort of the same. And the only thing that changed as well was that in the word stack, we started with these two variables, and then we arrived to 2, and then here to 3. And this is actually for the second execution. So once we see this, our job is to say, OK, we've gotten these state updates. What is the general form of this, right? And basically, that's how you can craft an invariant with control. You can just sort of come here and say, OK, we know we were here, and then we jumped here. That's concrete. And then, so first of all, what we're going to do is we're going to, well, first craft the thing, and then we're going to prove that what we craft is correct. So yeah, basically we're just saying, we have this state, and then we're just going from here to here, and then we generalized what we saw. We generalized what we saw here into a more abstract formula, and just saying, from I go to N, and then from this closed form, we go to this other closed form. The thing is, this is a claim. So maybe this is too detailed, but what I want you to get to remember of is this is a claim. What you're doing is you're crafting a state difference, and then you're actually proving that the state difference holds. And this is done via this claim instead of a rule. We're just saying, yeah, this is how the K execution cell is going to differ, to change. There are some stuff that we want to keep just to keep the rule actually provable in the sense that this is how we executed this program. Here is the main let's say source of reasoning that you want to have. So the main abstraction that we're doing is coming from what is written here to what is written here. And that's where the challenging part of crafting loop invariants comes, which is you have to understand your code, you have to reason about the properties that it has, and then you sort of go from this concrete difference to the general form that it should have. Then we have the same PC that we were executing with, and then some more stuff, and then some well-formedness conditions. And the thing is, what we're saying now is, hey, this can be turned into a rewrite rule. So this can be turned into basically just telling control, whenever you are at this program counter, whenever you are facing the loop head, which is this thing that we have here, just rewrite it to this, and then the general behavior of my loop is going to be this transition, right? And with this claim, what you're actually doing is telling control, prove me that this is correct. So this is not giving the user like you just write whatever and then control will just take it. you're actually able to take control and say, just prove that this state transition is actually accurate and that it works. And then you just, you can translate this into a rule once you have proven it correct, which basically means just taking a bunch of other constraints and putting it in the bottom. But basically, you end up in a loop in which you actually you have this state transition, and this captures the actual behavior of the loop of the while loop that we were facing with. Once you do it, you can actually prove the statement without any BMC depth, so it will be capturing the loop behavior in full. And that's how you basically can verify a loop with control. We have used in our engagements because also so we have been dealing with a very on the face kind of loop, but also, for instance, there are some loops that are inserted by the compiler, not with the recent. With the latest one, since we have now mcopy, but it was the case for I think it was from Solidity 0.8.24 previously. If you had a bytes memory argument, you will the compiler will insert there a loop that you will need to reason about. And so, for instance, this lets you reason about it in full generality. So I hope you are excited to try Kontrol. I try to show here from going from the basic use to actually show you an advanced example of how to use Kontrol. I think we have killer documentation on this. You can also have Kontrol in your CI. So please feel free to go to the documentation, read it, and we're also very responsive and active. So if you want to get in touch with us, feel free to come to our Telegram channel, to our Discord. We're more than happy to hear from our users. And so thank you very much for attending this talk.